It's very nice to be here. It's very nice to be anywhere, actually, at this moment. I've never...
Dark.
Thank you for finishing dinner so that I'd be able to talk. I've actually never been a dinner speaker before, so this is kind of a life milestone for me, so thank you for being a part of that. I was kind of reflecting on my favorite dinner time talks that I've gone to in my life, and a lot of them make you think, but not too hard because you're digesting. So hopefully I can hit that for you guys. Give you some stuff to think about, but not really put you on edge because we're just chilling. It's the end of the day. So what I decided to do. So you've been talking about large language models and game theory, which feel like they don't necessarily go together, but you're figuring out how to make that happen, and that's super cool. So I figured anything I could make up on the fly about that, you've already covered, I assume. So I'm not going to talk about that at all. I'm going to take a step back and talk about what I think we're trying to do more generally, what I think computing is about. And I think what computing is about is making it easier for us to tell computers what to do for us. And I think we're actually doing really well at that. We're making it easier and easier to do more and more impressive things. Stuff that we had no idea how to do just a couple years ago is now possible, maybe even easy. And so while we're doing that, I want to impress upon you to also think about making it easier for the people who are not in this room, right? The people who are not necessarily experts in computing and game theory and language and all these things. But everybody, my sister, just whoever. People need to be empowered to use their computers to do the things that they need to get done. And I feel like that power's kind of been taken away from them, and we have a great opportunity now to try to help everybody really engage with this powerful kind of thing. So my talk is getting computers to do what we want, programming meets machine learning. All right, so I'm going to say a bunch of things that you already know, but hopefully in this sort of post-dinner, my spouse calls it post-pharyngeal, like while you're digesting perspective, to just kind of reflect a little bit on some of this stuff. So for me, I like to think about computers as being kind of like people. People act in the world, computers can act in the world. So I'm going to just use a running example through the talk of tomatoes. Did we have tomatoes with dinner? Did anybody have tomatoes? There were tomatoes? All right, this is great. Okay, so let's say that you want to grow tomatoes, and maybe you don't know how to do that. Well, maybe you do know how to do that. Maybe you have a little something program-ish or something in your head that says things like, well, if the soil's not dry enough, then maybe you should water the plant. So this is supposed to be a person with this is a hose, a garden hose, that can then be applied to the tomatoes. All right, so she knows how to water tomatoes. That's great. She knows how to take care of them, make sure that they thrive. But I don't. And I might want to have tomatoes work out too. So what the heck am I supposed to do? So to me, oh, interesting. She disappeared. All right, so in the slides, there's that person with the hose is here, and she knows what to do, and she's going to somehow transmit it to me so that I can take care of the tomato plants. Right? So she's not going to do it for me, she's going to tell me how to do it. And so, I don't know, we could call that teaching. And somehow teaching lets you transmit a program from one person to another person, and that's actually pretty cool. I mean, I think a lot of people talk about how wonderful it is that humans are so smart, and this is why we get to do all sorts of cool things. And I guess that's true to some extent, but I think this is one of our superpowers. It's not just that we're smart, but we can actually take programs from one head and put them in another head and run them and spread them around, right? And that's incredibly powerful, because we don't have to be so smart. Just somebody else has to be smart and tell us what to do. All right, so if you don't know how to take care of tomatoes, I'm going to now teach you how to grow tomatoes. I found this little video online. She's going to just give us a quick lesson, all right? If we have sound, you'll hear it. If not, you won't, and I will have to maybe make the sounds on her behalf. So let's see if it works. Nope, there's music at this point. All right, so I'll take you through it. This is Ashley Lemon. By the way, great name for someone who takes care of tomatoes or plants in general. She's a senior biology specialist, in fact, so she knows what she's doing. And she's going to teach us how to water our tomato plant. All right, so that's what she tells us at first. You think it might be on now? No, we can just do it out of the computer speaker.
My volume.
There you go. It's all the way up. All right. So this is cool. So I can stop the video. Oh, crap. I can stop the video, but I can't restart the video. All right, so I'm just gonna let, oh, I heard two notes.
Hi, I'm Ashley, and today I'm going to show you how to water your tomato plant. The easiest way to determine if it needs watered is the finger test. Simply stick your index finger about an inch down into the soil. If you bring it out and it's dry, it needs watered. When watering a tomato plant, you want to make sure you don't water on top of the foliage, if at all possible. That can cause disease. Always water at the base of the plant and make sure it's a nice, thorough watering. This plant will love it as it has great big roots and they love a nice deep water.
All right, so that was the whole lesson. So what do you think? Did she do okay? Like, do you feel like you picked up a thing or two? You know, for a short video, I actually think that was pretty reasonable. So let's break it down a little bit and look at what she did, how she did it. So I would say that we can take all the different kind of mechanisms that she used and put them in a little 2x2 grid. So one of the things she did was she gave us explicit instructions. Stick your index finger about an inch down into the soil. Okay, so that was one of the things that she said. Another thing she did, though, is to give an explicit incentive. Not actually an instruction, but it's like, what is it that you're trying to do? And one of the examples of that is she says, that can cause disease. Now, if she's just telling you the steps for watering the tomato plant, that's not relevant information. That's a complete side note. But it actually is really helpful that she said that, because if now that the program's in your head and you're actually taking care of the tomato plants, and you see the disease, you'd be like, oh, I overwatered it, right? I know that that is an outcome, and I should try to avoid that outcome, so maybe I should actually back off on the watering. All right? So this is actually really useful information, even though it's not an instruction, it's not a thing to tell us to do, it gives us the ability to train ourselves to do a better job at it. All right, so the next part of the little 2x2 are examples. So she gave examples of instructions. She didn't tell us how to get the tomatoes out of the way so you can water the roots without the leaves, but you could see her do it. She took the side of her arm and she pushed the leaves away. Now, again, she didn't have to say it, and just the example enough was probably sufficient training that you could do it with the tomato plant that you've got. Now, maybe if it's up against a fence or something, you might not know exactly what to do, but you've got an idea just from this example of the behavior. All right, and the last bit of the 2x2 here is something I think of as example incentives. So she didn't. So again, the incentives are things like this is what you're trying to do, so you can actually monitor your own performance. But she told us some of those things, but she also showed us one of these things. This is not a great still frame. This is not her best face. But the frame, what she was saying, in context, this actually makes sense. So what she said at that point was, the tomato plant will be really happy, right? So she was kind of conveying through her own behavior that this is a good thing. You should make the tomato plants like feel like they've got enough water, right? So she's conveying the incentive, but through an example, through her own feelings almost, demonstrating her own feelings about it. All right, and I want to claim that this is pretty comprehensive. I'm sure this is a spark for people. I'm sure you can find things that are not part of my 2x2 grid, but a lot of, like, I've been thinking about this for a while, and a lot of things really do fit really nicely into this. All right, so one of the things I think is really cool about this is those 4 cells map onto pieces of a trite little saying that was published in Reader's Digest in the 60s. And it goes like this. If you're a teacher, as many of you are, or maybe will be, it goes like this. The mediocre teacher tells, the good teacher explains, the superior teacher demonstrates, the great teacher inspires. And this is kind of judgy. Because it really comes across as, right? Which is not really correct, right? Because if you have a teacher that just stands up in front of everybody and just inspires them, that's not helpful. Like, I don't want to know how to compile the program. Compile the program. No. You really want all these things, and they should be kind of working in tandem with each other. So that's kind of a key. And Ashley did it really well, right? So she had something in each of these boxes. She told us stuff. She showed us stuff. She showed us, or told us what we should be feeling or trying to do, and showed us what we should be trying to do.
Is this explainer itself telling, explaining, demonstrating, or inspiring?
I know, right? Like once you get into this mindset, it becomes very hard to tell anyone anything because you start to think, oh wait, that was an example. Oh wait, that was an instruction. So yes, so Ashley, like the fact that I showed you the Ashley video was an example. But this is kind of telling you this is a more high level kind of abstract version of it. And they work together really nicely, right? Because if you just do the abstract stuff, you might not be sure exactly how it plays out in the real world. But if I only show you the real world stuff, then you won't really know how to generalize it properly. So we'll see that as we go. And again, people can think of lots of examples of these. But I want to think about the notion that we should be thinking about telling computers what to do, maybe not so differently than the way that we tell people what to do. And here's what you need to know. We're going to convey that to the computer. So let's imagine that we've got a computer that is actually going to do the tomato watering in the sense that it's got sensors, things like, have there been rainfall, has it sprayed recently, what's the current temperature, what's the height of the tomato plant, things that you can actually measure about the world. And then it's got a set of actions, things like, well, I'm going to spray today, or I'm not going to spray today, I'm going to wait till tomorrow. All right? And so telling the computer what to do to take care of the tomato plant, at least as far as watering is concerned, kind of comes down to figuring out how to take these inputs and turn them into the appropriate outputs. So I want to say that those 4 boxes map really nicely onto the 4 ways we tell computers what to do. So telling is like traditional programming. We actually give explicit instructions. Do this, do this, do this, do this. Incentives, or explaining, corresponds to reinforcement learning, the sort of idea, or more generally sort of declarative programming, right? Where you actually state what it is you want the system to accomplish, and you leave the details to the machine. Demonstrating is supervised learning. I'm just going to give you lots of examples, and you should figure out what to do from that. And then this is the kind of the weakest box, but the inspiring is basically trying to pick up the loss function or the objective function from examples. So I'm going to give examples of all these things. All right, was there a question that was bubbling? Okay, so yeah, there's one.
Self-supervised learning is.
Well, yeah, I mean, so part of it is just framing, right? So self-supervised learning is a kind of demonstration,
Okay.
right? So the demonstration is the data itself somehow.
Right.
Yeah, I think that's maybe the best way to look at it.
Maybe.
Yeah. You know, and then you'd like transfer learn. Like there's definitely, you can find cracks in this. So don't try too hard. It's right after dinner. Why would you tax yourself like that? All right, so I think probably everybody here knows about programming. So this is what a program might look like for this tomato problem. Things like repeat forever. If it's not the case that there was, it rained yesterday, or I sprayed today, or yesterday, then I should spray today, otherwise I'm just gonna wait, right? So that's a really simple, like, if there's no reason to think that it's moist, I should spray. Which is probably not a bad rule, but it's probably also not great, because things like temperature are relevant, things like the age of the plant are relevant, but that's actually not terrible. So there's many different ways that we can express code like this. Tons of programming languages. There's sort of block languages where you can click things together, but they're all getting at the same thing, which is I'm going to tell you the instructions, and I'm going to put some control flow around it, so it's not just explicitly like do this, do this, do this, do this, but also things that can capture the context, things that can kind of compress the number of steps that you have to do so that it is simpler to convey. All right, so maybe this is the best way to tell machines what to do. What do we know about programming and people? Well, there's a literature on this. One particular example that I find compelling is an example from the 80s where beginning programming students were asked to do a bunch of programming problems, write down their things, and then people scored them. So one of the examples was a thing they called the rainfall problem, sort of vaguely appropriate for the whole tomato watering, but they didn't know that then. So we'll give them credit anyway. So the rainfall problem is, they say to people, a version of this. Compute the average of a list of numbers. The list is terminated by 99999. That's the whole problem right there. All right, right? So you're going to get a list of numbers. You should just keep taking in the numbers. When you hit a 9999, stop, compute the average, spit it out. Okay? That feels easy, right? Does everybody... Okay, maybe I shouldn't be so judgy. Like, does that seem easy? Okay, yeah, all right. I think that's kind of easy. And so the people who were running the study were kind of expecting everybody to do really well, but in fact, 86% of the beginning students couldn't do it. Like they had all the programming knowledge, all the pieces of this they had, but they couldn't put them together to make a flawless program. And there was much gnashing of teeth. There was much concern, like, oh, we're teaching computing all wrong, everything's terrible, we need to rethink how languages work, we need to think. So anyway, maybe we didn't ask the questions the right way. There was a lot of analysis of this result, and it continues to be interesting to many people to this day. But even if we put this aside, there's plenty of examples out there of professional developers writing buggy code that does terrible things. Crashing cars, crashing spacecraft, having power grids go down, having the entire internet go down. Like, bugs happen. Bugs, it's hard to write really good code. So, one thing I would like to tell you about, some new results that we're working on right now, is I don't think it's just the programming part. It's not just the weird symbols and the semicolons. I think actually saying what a task is, telling somebody what to do, is actually just hard. And so we decided that we would just leave the computer out and just have people tell other people what to do and see how that went. We'll see how that goes. All right, so we're collecting preliminary data, but we're finding that it's almost as hard as programming. In spite of the fact that you get tweets like this from earlier this year, the hottest new programming language is English. Because you can actually, and you can kind of do it, right? You can write in English. You can type to ChatGPT or something, and this is slightly post ChatGPT, right? You can type in a thing, and it'll spit out code. And that code sometimes runs. That's remarkable. It is, I mean, like, I make fun because it does write buggy code, but like it sometimes works, which is pretty amazing. Because like 20 years ago, 15 years ago, 10 years ago, maybe a year and a half ago, we didn't know how to do that. So this is pretty cool. But I do want to. My big caveat that I want to put on this is, yeah, okay, so English is a programming language. Turns out you can write bugs in English too, right? So this doesn't make the whole thing go away. It just makes it so that we have to be a little bit more careful. In fact, English is not as crisp or precise as a programming language, and so there's a whole new class of bugs that you can make. It's sort of like vagueness, right? You can't write a program and have it be wrong because it's too vague, but you can in English, and people do. So all right, I don't know if we want to get into the grimy details about this, but what we did is we set up. This is me and some collaborators at the University of Chicago. We set up a system where two people are recruited off the internet. One is called the sender, one is the receiver. We give the sender a really long story about, like, this is a task that I want you to get some help to do. And so an example is like, this is one of the examples that we actually use. You're a poet making poetry out of old books. Yada, 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 yada. Anyway, long story. Partly we made it long because we didn't want them to the sender to just look at that and just hand it over to the receiver, because making it long meant that they'd have to type it, and they're lazy. So they didn't do that. They did tend to get hung up on the detail. But anyway, the punchline is here. So determine if you can form your poem, or string, essentially, by optionally deleting letters from another string. So I'm going to give you two strings. And the question is, can you make the second string by deleting letters from the first string? So what we did is we conveyed that task with all this sort of fluffy stuff around it, and we said to people, okay, now here's two strings. Is this an example of something that you can make one out of the other or not? Does that make sense? So we wanted people to be the computer. We're going to give them inputs, and we're going to give them a program, which is our description, and we're going to wonder whether or not they can actually do the task. Okay. All right, and again, we recruited two people. One is the sender. The sender reads that and then has to type some stuff to the receiver. The receiver then is given reads that and is given some examples and has to then hopefully correctly answer T or F for this particular problem. Okay, all right. So this is our preliminary data, which presumably you can't just grok, because I couldn't just grok it. But what this is telling us is we ran lots of versions of this with lots of different problems and lots of different, like, for example, the sender has programming experience. The sender does not have programming experience. The receiver has programming experience. The receiver does not have programming experience. All these different variations we collected data on. And, you know, I think some really interesting stuff. This is preliminary data. This is not published. Don't stake your careers on any of these statements. But this is what we're starting to see in the data. First of all, programmers are better at telling people what to do for these tasks. I feel good about that. I feel like right? Like we can pat ourselves on the back. Like we learned something. When we learned a program, we actually learned something that translates not just to computing, but also for telling other people to do computing. Yeah, maybe that's not so surprising, but I don't know. That was warmly received by me. Programmers were actually better at following. Oh, that's supposed to be our directions. So we gave them instructions, and the programmers were better at following our instructions than the non-programmers. Why? Well, partly these are programmy kinds of things, and we're programmy kinds of people. We probably expressed it in a way that's happy for us people. But anyway, that's another thing we found. All right. We also ran versions of this task where the two people were recruited, and in one case, the sender writes to the receiver, and then the receiver just has to do the task. But in another case, the sender writes to the receiver, and the receiver can say, well, what? Wait, explain this part again. Right? So they actually get to have a chat. They go back and forth, and they confer until they finally decided, okay, now I understand the instructions. Great. We terminate the connection, and we give them the test problems. Okay? So maybe not surprisingly, being able to ask clarifying questions helps. Interestingly, it helps both. Because we ask, after the communication is done, we ask the sender and the receiver a bunch of test questions. The sender does better at the task having gotten clarifying questions from the receiver. Now, anybody who's taught knows this, right? Because you can know something and you can do well on the test and everything, and then you get up in front of a class to teach it and you're like, I don't know this at all. I need to really understand this. And then you go and you understand it and you explain it to people and you go back and forth, and it's like, oh, I'm so glad I taught that to me. Right? So we're seeing that on a micro scale with these tiny little problems. So that was pretty neat too. And another thing, taking it back to Ashley Lemon, is examples help. So in one condition, we just let them write the text. In another condition, we said, and as part of your text, include some examples of what inputs and outputs look like. And these examples help really kind of solidify what the question is. Now, I would love it if all these were like 0%, and then when you do it, it's 100%. It's not. They're relatively small differences, but they seem, well, we'll see if they're consistent or not as we get more data. But that's kind of the story there, that even in people talking to other people, these patterns seem to be relevant. Now, another thing that we're doing, though I don't have any of the data for it, is taking the explanations that people generated for other people and feeding them to ChatGPT. And then asking ChatGPT to do our test problems. And the question is, which of these explanations work the best? The ones that went through the clarification process, the ones that didn't, the ones that were written by programmers, the ones that are not. So there's a whole other dimension to this pot that we're going to have, which is how does the language model do? In preliminary results, it seems like it's sort of like people. Like if a person writes a really bad explanation that another person can't understand, the language model also can't understand it. Right? It's not that they have this magical ability to read between the lines and get it right every time. It's muddled input, garbage in, garbage out, right? So when people explain it in a way that's difficult to understand, then it struggles. I don't know. I mean, like part of this for me is the subtext of all this is we need to do a better job of getting people to think, right? Like we want people to use computers better, but part of that is just getting them to think more clearly, right? And I think that's part of what the programming training forces you to do. You really have to grapple with this fact that you need to be careful. You need to think about what could go wrong and how it can go wrong. All right, I wanted to mention another result just quickly. So a thing you could say, not that you would, but it's something that people might say is, well, but programming's hard. If we just had an easier way of doing programming, everything would be okay. And so there are some user-friendly schemes like trigger action programming. So I don't know if you've had any experience with this, but trigger action programming, you write rules like this. If rain forecast tomorrow, then delay watering. So they're sort of like little mini production rules in a way. But there's a whole bunch of websites that let you play with this. So if this then that is one. I know Amy's played with this. Yeah, and you had your dad play with it, if I'm not mistaken. Yeah, okay. So it's sort of interesting because it's definitely easier than full-fledged programming, but it's more limited, of course, because you can only say things in this form. Most of the sites will let you do conjunctions in the if clause, so you can actually take a couple of the different conditions and add them together. But anyway, so there's papers about this in like the CHI conference, like Computer Human Interaction Conference, showing that, yeah, people can kind of do this. Like people with not a lot of programming experience or no programming experience do okay at this. But it depends how hard you push them. So even this trigger action programming can be hard. What we found is that 40% of users erroneously interpret trigger conjunctions. So when there's an actual conjunction in the if part, people can write those, but they have no idea what they mean. And so they are not inclined to write the right thing because they don't really know what it means. Because the semantics gets a little bit tricky. Okay? So anyway, even simple programming can be hard. All right, so that's the end of the tell box. Right? So we talked about programming. I want to talk about reinforcement learning next, the explain box. So this has been traditionally my area of interest, and I think if you're thinking about game theory from a utility perspective, like a lot of the whole utility perspective is we're going to think about what the objective is, right? We're going to give the incentives, and well, that's all we have to do. Like the rest of it just works itself out. So I still like this. I really think this is a good idea. You know, computers, after all, are powerful. Say having to give all this explicit instructions is very limiting. So instead of telling them what to do, we just tell them how they'll be evaluated, and everything should be fine. And there has been some success with this sort of approach. So these are Atari video games, the quintessential problem that humanity needs to solve. At least when I was 8, and I played these a lot. Not this one so much. This is all very weird. But yeah, these guys a lot. So what's neat is that you can actually set up a program where you define the objective to be maximize the points in the game. And then you can give the screens to the computer, and the computer can decide which actions to choose to maximize the score. And it plays, on average, across a whole bunch of games, better than a person who is given a very limited time to learn to play the games. The computer, of course, is given like the equivalent of 100 years of just sitting and watching Atari. You'd be sad a little bit if it didn't learn to play the game well. It's like, what have you done with your life? All right, same thing with Go. Go is very impressive, but again, it's like 70 years of nonstop Go, no eating, no sleeping. But at the end of that, it actually plays some wickedly good Go. So this is neat. All right, so in principle, we can use reinforcement learning, or this sort of objective-based programming, as a way of telling machines what to do, like for watering tomato plants. So the whole tomato plant program might look something like this. Just repeat forever. Use however you want, we're saying to the computer, information about the rainfall, the temperature, the spray, and the height, so that you can choose between these two actions with the goal of, let's say, maximizing the height. Okay? So you figure out how to water the plants. This is how you measure performance. Go to it. And I don't know, 15 million tomato plants later, you've got a tremendously good watering program, right? Very subtle. It handles all these special corner cases. It's awesome. I don't know. I think that's kind of cool. Again, it's something that's probably that you can't really use locally because these algorithms tend to be quite data hungry at this point. So there's not as many examples of this kind of approach to telling machines what to do as there is for programming. There's programs written by humans run a lot of modern society. This less so, but there's a couple examples that are kind of neat. One is the folks at Nest, the thermostat people, set it up so that the thermostat is actually kind of learning about the thermodynamics, or is that the right word? I'm going to say thermodynamics. Thermodynamics of your house. Like, if we turn up the heat and it's this temperature outside, it's going to take this long for your house to actually get up to this temperature. And it learns to do that by, like, turning the heat on and off, turning the air conditioning on and off, and it figures it out, and it ends up being much more efficient. Once it has that information, once it understands your house, it can actually, given your preferred temperature, it can try to hit that, close to that, while minimizing energy use, which is pretty slick. Something that learning is really needed for, because you can't, in the factory, they can't know how your house is going to respond to the input. So there has to be some learning kind of in the field. So I think that's a really cool example. This example is cool, but also scary. YouTube recommendation uses some of these ideas where they show you a video and see if you like it, or maybe like is the wrong word, if you sit around and watch it all the way through, and if so, it recommends other videos to you that might also get you to sit and watch for a long time, and then before long, you're a terrorist. So that's awesome. They make a lot of money from that. All right. So and I learned about one really recently from folks at Amazon. Apparently they're using this kind of approach to run their supply chain, to figure out how much of each product, like how many Ace brand toothbrushes in green do they need to keep in the warehouse in Metuchen, right? So they've got all, I don't know if there's one in Metuchen, but that's a New Jersey word, I like it. So they have to figure out all this for all these different products. And so they do this with a kind of a reinforcement learning approach. The goal is to maximize this kind of crazy thing that they made up that has to do with profit and not being able to fulfill someone's order when they make it, to say, oh wait, sorry, it's going to be 2 weeks before you get that. Like there's an internal cost to that. And so they make up an objective function, they're actually optimizing this objective function, and they're starting to use this to actually stock their warehouses. So I think that's pretty cool. All right, so I do want to point out that all is not happy in the sense that these can lead to unexpected consequences. And so this is an example, if you haven't seen this example, it's fun for, you know, especially for a dinner time talk. So this is a video game example. It's a boat racing game where we're the white boat and there's these other boats and we're supposed to go around the track and we're trying to beat the other boats. What could be easier? All right, but it turns out that to make the game more interesting, there's also various kinds of points and boosts and things that you can hit along the way. But so there's advantages to maybe taking a little bit of a side trip and grabbing some extra points. So they set this up as a reinforcement learning problem. They said maximize the points. That seems reasonable, perhaps. And so what does it do? Does it win the race? Well, it definitely learns. It learns a strategy, and the strategy looks a little something like this. Notice the arrows. We're not going the right way. We're really not going any way in particular. We're bashing into some other boat. It looks like it's just bad at this game, but it's not. It's actually really good at what it was told to do. So now it's settled into its pattern. So it's in a harbor, off the track, running around in a circle, smashing into the side, but also into these three things, which give it points. So it's getting those points, and it times the circle just perfectly so that they regenerate just as it rams into them again. Right? So it's just over and over again. It's like destruction, mayhem, points, right? And so, what do you think at this point? You're like, well, I didn't tell it to do that, so. Or you could be thinking, okay, well, if I actually programmed a self-driving car this way, people will not be happy with me, right? So this is the issue, that you can get kind of divergence between what you want it to do. You have to write down the way you want it to do it, and then it does that, but maybe it doesn't do what you originally wanted it to do. Bad behavior, even though it's getting a better score. Sorry. All right, so, but nonetheless, I think that there's something to this, and so we've been running some new experiments. This is also hot, like on the train on the way here, I'm like writing to the students, like, can I get a screen grab of this? So this is also hot off the press and not published or anything, but I thought it would be fun to share it with you. We're running this experiment where we put together a little simulated house robot. I know, coming right after the boat smashing thing, like I can see, you're picturing like, and then the robot goes on a rampage, and it breaks all the walls, and it eats the toys, and kills all the children. So, it's none of that, it's fine. So just everybody relax for a second. So there's a couple rooms in the space, there's some toys and so forth, and then we gave people the opportunity to program this using a kind of a block interface. But we created 4 different block interfaces. One that's kind of more like programming, one that's more like trigger action programming. But it turns out you can kind of program a robot with trigger action programming. That was surprising to me, and it's kind of neat. And then one that's more like reinforcement learning, where what you have to specify is what it is that the robot's trying to accomplish. So you have to translate your task into an objective and see how that goes. So we recruited people off the internet, we had them do this, and we made up 3 tasks. One is avoid the person. You can't see the person in this one, but there's a person that sort of randomly moves around. What you're supposed to do is, if I'm the robot and I'm in the same room as the person, I should go into a different room. Task 2 is take a toy from a random room to the playroom. So we initialize it with a toy someplace. It has to basically find the toy, wherever it is, and pick it up and bring it to the playroom and drop it off. And then the third task is move all the toys from one room to another. So like in this case, there's a pile of toys in the kitchen. They don't belong there, they belong in the playroom. So the robot should go to the kitchen, pick up a toy, bring it to the playroom, go back to the kitchen, pick up a toy, and so forth. Okay? So relatively simple programming tasks, but the way you express the task in a programming language is different in these different modalities that we provided people with. And so what we found is for this task 1, avoiding the person, reinforcement learning and TAP, trigger action programming, the red bar, like the percent of correct solutions was highest for those two. But for the middle task, which was fetching all the toys, no, there's a toy that's lost someplace, finding it and retrieving it. It turned out it was kind of hard to say that in trigger action programming. People did really terrible. But it was actually much easier to specify it as an objective. It's like, there should be no toys in that room. Or, yeah, essentially, there should be no toys in any of the rooms except for the target room. And then for the third task, no, that's the third task. For the second task, it needs to have gotten the toy and put, so the goal in that case is be in the target room with the toy. And people found it pretty easy to express that. And then the third one, it was easiest to use the trigger action programming or the RL, but the programming way of doing it, actually specifying steps, was hard for people. Not so hard, but harder than the other ones. So it's interesting, right? So it's for people, depending on the task, they kind of are best off expressing it in different ways. And it's not exactly clear how to put that into the interface, right? It's like, give them all the choices? That might be overwhelming. Pick the right choice for them? That is probably hard. So we're still in the process of trying to figure out how to do this. But sometimes reinforcement learning as an end-user programming language seems to be working out. All right, so yeah, what should I be targeting for stopping? You're already 5 minutes past. Okay.
Like 8, I think we should end by 8.
Okay. All right.
I'm just gonna
The shuttle is
check
at
on
8.
All right. So the next box is supervised machine learning and self-supervised learning. So we can go through that fast because you've already been thinking about that a lot. It's about mimicking the expert. You give it a data set and it learns a rule to produce the action from the inputs. You can do that for the tomato plant example. People have done it for lots of other things: spam filtering, face and image recognition, context-sensitive grammar checking. It still just tickles me when the computer gets suggests the right word. If I use that same word in a different context, it's fine with it. I don't know. I guess I'm old, right? Like that, they couldn't do that before. They're doing this really well now. So this is 2 sentences I made up. I've hired many talented people for domestic help. It should be many, and of course, not of course, but what it does is it puts a wiggly line under it and says, I think you mean many. Okay, great. But if I put that same word, I've hired a talented Manny for domestic help, it's like, oh yeah, that's fine. Manny is like a male nanny, right? That's a word that some people use. If you don't know the word, that is a word that some people use. We can talk about whether it's appropriate or not, but anyway, I used it as all right, so, right, almost all the same, like if you just treat this as a bag of words, they're really indistinguishable, but it really is understanding something about the sequence enough to be able to say that's okay and that's not okay. And I didn't cherry pick this example. I mean, I worked really hard on this example to get the words to work, but it's really consistent, and you probably have seen all this, so I will not belabor it. One of the problems with these machine learning systems is they can sometimes latch onto the wrong features, right? And this is part of the reason why we have to give them boatloads of data before we can really kind of see a consistent output. But an example from the literature is they were trying to train a husky versus wolf system. Is it obvious to everybody which ones are the wolves and which? Okay, all right, there's some nods. I thought it would be harder, because I look at huskies and I'm like, that's a wolf, right? But when you see it with the real wolf, you're like, no, that's a wolf. Like, there's something very deep inside me that just doesn't want to be. I mean, there's a reason that fairy tales the wolves are the bad guy, right? That's a lot of fierceness. So what's interesting is you train a system on a bunch of just arbitrary pictures of huskies and wolves, and what it learns is if there's snow in the background, it's a wolf. And if it's on a couch, it's a dog. It's a husky. And that works, right? You can actually get very high performance on the testing set and on the training set, but then you apply it to these new examples, these slightly out of sample examples, and it goes wrong because it's not really paying enough attention to. Yikes. Okay. So, all right, and so I think this is worth really thinking about, right? Because we know what the rule is, or we know something more about the rule than we can tell it just with giving it lots of data, but we're not allowed to. Like, there's no input into the machine learning algorithm that says, No. If it scares, if it gives you nightmares, it's a wolf. Like, you should just pay attention to that. I mean, okay, all right, enough of that. As we've thought about a lot, unsupervised language learning or self-supervised language learning is a similar kind of thing, where we can actually use the sequence of words as its own kind of training game. And as everybody knows, there's kind of a surprise that comes out of that. I was surprised. Given enough training on just predicting the next word, you can build a system that can write in different styles, it can translate languages, it can have a conversation with you, it can answer questions, solve some basic problems. It's not actually a very deep thinker, but if it's a problem that it's seen before, it does a pretty good job of recognizing that and answering it. It can take direction, you can kind of tell it to do some activity, and it can write programs. Wait, that was the thing we were just thinking about a couple slides ago. Maybe this is done. So remember the rainfall problem? I gave the rainfall problem to ChatGPT. Write a Python program to compute the average of a list of numbers terminated by 99999. And it's like, well, first, and you know, the ChatGPT rhythm, right? It's like, first let me restate the problem, then I'm going to give you a bullet list, and then I'm going to summarize what I said. So it sets it up, it writes the code, and then it talks about it, and it kind of assesses the code afterwards, but I left that off. And this is code that's really close to being right. Sometimes, depending on exactly how I word the prompt or the question, it'll compute the average. Like the control flow here is basically correct. When it goes to compute the average, sometimes, like if you say it as a list of numbers terminated by 99999, don't include the 99999 in the average, which is redundant. Like, you shouldn't have to say that. It's kind of, maybe kind of obvious, but if you say it, then it will sometimes divide by length minus 1. Which is wrong, right? It stops, it doesn't include the 99999, and then it doesn't include, it gets the count wrong. It gets the count 1 off. Here, it's mostly correct, but there's this weird insistence that it needs to be an integer, which is nothing in what I said. Now, you might not catch that. You would probably catch that. But like somebody, if they didn't already know how to write Python, it's not so obvious. It's kind of buried in here, this basically just input checking, but it forces it to be an integer. So that's not what I wanted. But it's really close to what I wanted. All right, but I really do think it's conceptually weird that we wanted to write a program to predict the next word. We didn't know how to write that program. So we used machine learning to write that program. And that program, once written, can itself write programs. Right? So that's really interesting. I would not have thought it could do that. And so this is helping some people, especially engineers, write code faster, especially for code that is tedious but standard, because it's got lots of examples of those. For people who are less good, like end users who are not programmers, they're less good at spotting bugs, this is maybe not a great tool for them. All right, and then the last box, inspiring, where the idea is to use demonstrations to actually infer an objective and that you can then maximize in other scenarios. So, yeah, maybe I won't go into this. I'm not going to go into this, because you guys need to go to bed or whatever. So, anyway, we can infer things like reward functions just from examples of behavior to say, well, what reward function explains the behavior that I saw? Now that I have the reward function, I can apply it in new scenarios. And folks at Google have actually used this idea, this inverse reinforcement learning idea, to figure out how to give better driving directions. Right? So usually the driving directions will do things like minimize the time, the expected time, or minimize the number of left turns, because everybody hates left turns, except for, I guess, in Britain, where they hate the right turns. I don't know, whatever. But it turns out that different places have different preferences and different roads for different reasons, and so they actually trained on every road, 360 million road segments. They did inverse reinforcement learning on it, and they're giving 10% better directions in Singapore, 13% better directions in Miami. So this is really neat. It really is, like, they've scaled this up massively from, what I think of as like, that was already big. All right. All right. So the kind of lesson that I want to leave you with is the notion that if we think about Ashley and the way that she was telling us to take care of plants, she combined telling and explaining and demonstrating and inspiring all into one mishmash. And they all these different things have weaknesses and strengths. And by combining them, you get kind of this mishmash of complementary strengths and weaknesses. And the way that we build software at the moment are typically mutually exclusive. We'll do machine learning or XOR programming, not AND. And I think that's making it harder for us to tell machines what to do accurately. There are some emerging examples that I'm not going to go through because I probably made too many jokes and that took up time. But I'm sorry.
Where do jokes fit into the?
Yeah, which box is the joke? It's in the back. All right. Right. Perspiring. All right. So, so I'll do one last example. This is a thing that there isn't really systems that do this yet, but you can kind of sometimes get ChatGPT to do it. Which is, I gave the following query to ChatGPT. Since we're at DIMACS, it's a discrete math example. I thought that was fair. So I said to the computer, literally, make a list of numbers that aren't prime. Okay. There's lots of ways to interpret that, and I had one particular one in mind, and it wasn't that. All right. So it came back with the list 1, 4, 6, 8, 9, 10, and that's not what I wanted. Okay. Well, I could have just been clearer, but let's just take it as it is. That's kind of giving it a rule, but the rule was not a great rule. Then I said, separately, I had to clear it because I've been bitten by that. Like, it remembers things from the previous, like ChatGPT will remember things from the previous interactions and like information leaks. So I flushed it, and then I separately said, make a list of numbers like 4, 6, 8. Because what I wanted was 4, 6, 8, 9, 10. So I didn't want to include 1, because what I really wanted were the composites. And 1, as we know, neither prime nor composite. All right, so what did you think it says in response to that?
10.
Yeah. Yeah, it's like, oh, that's the even starting from 4. It didn't say that, but it listed the numbers. 4, 6, 8, 10, 12, 14, and so on. Like, no, that's not what I wanted either. What if I just literally take those two things and string them together? Make a list of numbers that aren't prime, like 4, 6, 8, and so on. Combining the example and the rule, and it gave me what I wanted. Let's do that, right? Let's make it easier to tell computers combinations of these different mechanisms. And that's my punchline. So, thank you.